Our speaker today is Elena Pavelescu, and she will speak on Maximal Linklessly embeddable graphs. Thank you, Elena, for joining us, and the floor is yours.
Thank you very much for the opportunity to talk. The work I'm going to present today, it's joint work with Andrei Pavelescu, who's also here at South Alabama, and Ramin Naimi, who's Occidental College. And I'll talk about maximal linklessly embeddable graphs. So the talk today will be focused on spatial graphs. So there'll be a lot of 3D visualization. There will be some combinatorics. I hope you will enjoy the presentation. So I'm going to start with. Okay, I'm going to start with a baby case for now, just to give us some motivation from where the problem of maximal linklessly embeddable graphs started. So we're going to consider graphs which are finite, so a finite number of vertices and edges. There will be no multiple edges between any two vertices, and there'll be no loops. So these are what we call simple graphs. And I'm going to start with this baby example, the planar graphs. So a graph is planar if it can be drawn in the plane without any edge intersections. And I gave you an example here. For example, this graph, it's a graph on 5 vertices, and it has some number of edges, no double edges or loops. And you see, I was able to draw this graph in the plane without any edge intersections. And when I say that, of course, I'm allowing the edge to kind of meet at a vertex, but I'm not allowing the edges to intersect in their interior. So this is an example of a planar graph with 5 vertices. And so it's this is a planar graph with 6 vertices. I drew some edges here. And again, I was able to take this graph and to draw it into plane without any edge intersections. So both these are planar graphs. A maximal planar graph, or what we call a triangulation, is a planar graph such that it's planar, but the addition of any edge will constitute an obstruction for it being planar. So if you see here in this graph, the graph with 5 vertices, this is almost a complete graph on 5 vertices. So I'll just label it here K5, but I will have to amend this labeling. So I have the 5 cycle on the inside, on the outside. I have the 2 diagonals here. I have this diagonal, but it's drawn on the outside, and the other diagonal. But I think I'm missing one edge there. I guess I'm missing. No, sorry. I'm sorry. I'm missing exactly that edge over there. So the 2 diagonals from this point are drawn, but on the outside to make the embedding planar. But I'm missing that edge there. So this, in fact, is K5 minus an edge. And it's not hard to see that this graph, or to prove that this graph is in fact, it's maximal planar, which is a triangulation. If you look at all the faces in this embedding, all faces are bounded by 3 edges, so all faces are triangles. And if I were to add this extra edge that's missing, I won't be able to do that without intersecting at least one of the other edges. So K5 minus an edge is a triangulation of a plane, or a maximal planar. Now, so is this graph here. This has 6 vertices, and then I'm drawing the edges. Notice the plane is again triangulated. And this is also a triangulation now with 6 vertices. Now, I'm bringing this up because there's a property of these triangulations, or maximal planar graphs, which says that any planar graph, any triangulation with n vertices, has precisely 3n minus 6 edges. Okay, so for example, I could take, if I count here the number of edges, let's see, we have 3 on the inside, 3 on the outside, that makes 6. And then I have the diagonals on the inside, that makes 9, which is exactly 3 times the number of vertices. Wait. So I have 3 on the outside, 3 on the inside, 3 connecting the inner circle with the outer circle, that's 9, and then 3 diagonals, that makes it 12. And that's exactly 3 times the number of vertices minus 6. So it's true for this example, but again, it's true for any other triangulation of the plane with 6 vertices. So we keep this in mind as we move forward with our discussion. Now, the next ingredient I want to talk about is the idea of a minor of a graph. So a minor of a graph in this construction is defined as a graph obtained from G, from the given graph. The minor of G is obtained by, it's a sequence of vertex deletions. So what I mean, I'm focusing on a particular vertex in that graph, and I'm deleting it together with all the edges that are adjacent to it. So this lower graph, it's a minor of the upper graph obtained by a vertex deletion. I can do an edge deletion. This highlighted edge in pink, it's deleted, so I get a subgraph. So as in the first case. And there's also edge contraction. Edge contraction means I'm going to highlight an edge, and I'm going to contract the endpoint. So I'm going to bring one endpoint to the other. If you think about it in the topology, I'm literally quotienting by this edge. So I'm going to drag these vertices to each other, identify them to a new vertex by contracting that pink edge. Now, when I do this in the picture, you see I have a double edge created here. The edge that was the upper one, that's a double edge. And then this edge, the contraction will create a double edge. But within the contraction, I'm going to after I contract, I'm going to erase any double edges because I want to keep the graph simple with no double edges or loops. So these are the 3 operations that give you minors. Of course, a whole sequence of these will give you minors as well. So you can do maybe a contraction followed by a vertex deletion or edge deletion. So you build a whole family of minors for the graphs. Now, there is a very important theorem in graph theory called the minor theorem, which says that in any infinite family of graphs, there exists 2 graphs such one of them is the minor of the other. This is by work of Robertson and Seymour, spans over 500 pages, over 2 decades. So if I have an infinite family of graphs, there's always one of them which is a minor of the other. And so let's consider, we're going to relate this to our topological properties, in particular planarity or other properties that we'll be discussing about. So let's consider a property P on the set of graphs, which is closed under taking minors. For example, planarity is such a property. If I go back to the earlier slide where I had a planar embedding, so not only planarity is closed under taking minors, but even the embedding, it's preserved. For example, if that's my graph to start with, if I delete this edge, if I take this minor constructed by deleting this edge, I still get the planar graph. If I delete a vertex together with its neighboring edges, I still get the planar graph. I can see that the embedding is still there, the planar embedding. And if, for example, I contract that edge, which means I'm bringing the 2 vertices close to each other, then I'm also getting a planar graph. I might have to delete double edges, but I still have the embedding there. So planarity, it's such a property, by which I mean it's closed under taking minors. So let's build this family of graphs. We want to apply this theorem to a property. We're going to consider the set of graphs, which I'm calling E of P. So it's a set of graphs pertaining to this property. These are minimal graphs which don't have the property P. So for example, which means that the graphs in this set don't have property P, but if I take any proper minor, if, for example, if I delete an edge of this graph, it will immediately, the minor will have property P. If I contract the vertex, if I contract an edge, or if I delete a vertex, all the minors will have a property P. And so, for example, this will be a finite. This will be the property of graphs which are not planar. It's an infinite family of graphs. Okay. This e to the p, it's the minimal graphs within this family that don't have property p. And I claim that this set is finite. Okay, this set EP is finite because if this set were not finite, with a minor theorem would mean that there will be two graphs in the set such that one of them is the minor of the other. But the smaller graph, the minor, because these are minor graphs without property P, this is not possible because the minor of the bigger graph will have to eventually have property P by the way we defined this set. So this set e to the P has to be finite. And so the conclusion here is that if you have a property which is closed under taking minors, there are finitely many such graphs which are minor minimal with not having that property. This is called a set of excluded minors for the property P. And one example here, since we talked about planarity, a graph is planar. The excluded minors for the property of being planar, we know that they make a finite set. The set of excluded minors are exactly K5 and K33. So this is by work of Kuratowski and Wagner. K5, it's the complete graph on 5 vertices. K33, it's the bipartite graphs where the partitions are 3 and 3. So these are pictured here. So this is the entire set of excluded minors for the property of planarity. Now we want to take this to a different property. So all this discussion, and the property that I'm going to focus on today is that of linklessly embeddable. So there is a bit of geometry behind, or topology behind this. Let me explain what this kind of graph is. So if I have two curves in space, two disjoint curves in space, they will form what we call a trivial link, like here, if you can literally take these two curves and separate them. So I can now take this curve and kind of separate it. They're not tied together. A technical definition would say that you can put a whole S2 sphere around one of the components, such that, or a whole 2 sphere, such that one of the components sits in the bounded region and the other component sits in the unbounded region. So these two curves are unlinked, or they form a trivial link. Now, different from that, it's what we call a non-trivial link. So curves which are really linked. And I have an example here. You see the one of the curves kind of goes backward, it goes in the back and then in the front. So what you get here, it's kind of this, like a chains within two links within a chain. They need to stay together to keep the chain in one piece. So such two curves form, or if they sit in this position, we say they are a non-trivial link. Now, how do we take this picture and put it into a graph? I have a graph which I'm going to imagine. Now, it may not be planar, so I might not be able to draw it in the plane, but I can imagine just thinking about the points, the vertices of the graph as points sitting in 3D. They could be many or few of them. And now the edges, they don't have to be straight segments, but the edges are any curves connecting these points in 3 space. Now, if I want to give it a bit of a perspective, I'm going to draw that. This edge goes in the back of that edge. So there's a projection here on the plane, but I'm marking the overstrands to see where the curves really sit in 3 space. Okay, so you can imagine kind of this projection lifts to 3 space and you give it a 3D perspective. Now, within a graph, you can identify, you have cycles of the graph. The cycles of the graph within such embedding, here's a cycle of a graph. That's a curve which is maybe piecewise smooth, or it's a curve embedded in R3. And here is another maybe cycle of the graph. So I have that one there. I'm kind of seeing it's the bounding a disk, and I have that one there bounding a disk. So these 2 cycles within this embedding are not linked because they sit away from each other. So if you can find an embedding of the graph in the 3 space such that any 2 cycles, any 2 disjoint cycles when compared sit like this, or they don't link, then that graph, it's called linklessly embeddable. You have an embedding where there's no non-trivial link. In opposition, a graph is intrinsically linked if every embedding contains a non-trivial 2-component link. So any way you embed it, there is a pair of cycles which link non-trivially, maybe like this, or maybe in a more complicated way by one of the strands wrapping around the other more times. So linklessly embeddable, it's where you have no non-trivial links. And if it's intrinsically linked, you cannot do without having trivial links. So let me give you a quick example here. I took that graph, the completed graph. I want to make this a bit bigger. Okay, so here I'm showing. I'm not doing well with this. Okay, here I'm showing 2 embeddings of K6. Okay, so I put in all the edges. And you see, I did the overstrand and an understrand to show you that, for example, this edge sits more towards us as opposed to that edge, which sits all the way in the back. And if you, for example, focus on these 2 cycles, these 2 cycles are 2 disjoint cycles, and they're clearly not linked in this embedding. And you can find other ones in here which are not linked. But if you look at this highlighted green and highlighted orange cycle, you see how the highlighted orange kind of comes from above, from below, goes above. And these 2 cycles link in the same way the other non-trivial linked here. So these 2 triangles are linked. They cannot be separated away in the same way these other 2 can. And here, this is a different embedding of K6. And again, you see that the green cycle links the orange cycle. There's no way to separate the 2. So these 2 are linked embeddings of K6. Now, we don't know that it's possible that there is a linkless embedding of K6. So this doesn't say much about K6, except that maybe we get familiar a bit with what linked versus non-linked means. Okay, so now here, maybe the parallel is linklessly embeddable. It's in a way the nicer one, like planar. And intrinsically linked, it's the more complex one, like non-planar. Well, this property of being linklessly embeddable is in fact closed under minors. Okay, so as we showed earlier, any property that's closed under taking minors has a finite set of excluded minors. In the same way we had K5 and K33 for planarity, we know we have a finite set of excluded minors for linkless embeddability. And by work of Conway and Gordon and Sachs, and then Robertson, Seymour, Thomas, we know exactly what the set of excluded minors for the nil property is. And this set is highlighted here. The set of excluded minors is what we call the Peterson family of graphs. We start with K6, which is the complete graph of 6 vertices. And we build this family of graphs. They are related by the following property. I take a triangle in for example, K6, and I'm replacing that triangle with what we call a Y. I'm going to put a point inside the triangle, and I'm going to connect that point, the new vertex, with the vertices of the triangle. And at the same time, afterwards, I'm going to remove the 3 vertices of the triangle. So I'm replacing the triangle with a Y. This is what we call, in this direction, a triangle Y move. And I can also do, if in my embedding or in the graph, I have a vertex of degree 3, I can also do the reverse operation. I do a Y triangle move. So these graphs are related by such moves. If I do a triangle Y move on K6, I get this, which we call G7. I can do a couple of triangle Y moves in 2 different ways, and then I get new graphs. Now, if I start with a 3-partite graph, K331, and I do a triangle Y move on that, I get this, or I do a Y triangle that direction, and then I keep doing triangle Y moves, and we finally get the Peterson graph, which you might know from other context. But this is the family of, it's called the Peterson family of graphs. And by work of all these mathematicians, we know that this is exactly the excluded minor set for the linkless embeddability. So the problem in terms of checking if a graph is intrinsically linked or not, it's kind of clear. We're just looking for minors and see whether it contains any of these minors. And if it does, it's intrinsically linked. If not, it's not intrinsically linked. In the same way, we had K6 and K5 from K5 and K33 from before. Now, I want to draw your attention to these couple of graphs, K6 and K331. These graphs, K6, you obtain by taking K5 and adding a vertex to it. I'm going to call this a cone because the new vertex, so I'm adding a vertex. How do I add a vertex? I take a K5 and I add a new vertex, which is connected to all the vertices of K5, and I get K6. And in the same way, the K331, which is also an intrinsically linked graph, part of the Peterson family, is obtained by taking K33 and coning over with a new vertex. What this means is I take a new vertex and I connect it with all the 6 vertices in K33 from before. I'm highlighting this too because if you remember, K5 and K33 were exactly the 2 graphs that were excluded minors from being planar. Okay, now we know how to decide whether a graph is intrinsically linked or not. And I want to move on.
Quick question.
Go ahead, Sandra.
Yeah. So if you just so is Peterson the only cubic graph in that family?
I think so.
So if you're thinking like minimally three connected graph or just the cubic members of the family, then that is equivalent to essentially excluding Peterson graph.
Say that again. If I'm looking at.
So if we suppose we want to know exactly the structure of this excluded minor class, as in what are the infinite families in it, etc. Then three connected. So then it would be equivalent to the problem of trying to figure out the structure of the graphs with no cubic graphs with no Peterson minor.
Exactly.
Okay.
Because it's the only minor that would potentially appear within such a graph. Okay, so now I highlighted a property of planar graphs before, having to do with a number of edges. And we looked at so-called triangulations. We said that every triangulation with n has the same number of edges, 3n minus 6. Those were maximal planar graphs, maximal with the property of being planar. Now, I'm going to look among all the graphs that are nil, or that have linkless embeddings, I'm going to look at those that are maxnil. So they are maximal with the property in the way that they don't have a proper subgraph of the same order. So, or in another way, if you add any edge to it, it will fail to be nil anymore, so it will become intrinsically linked. Okay, so maxnil means any added edge, it creates intrinsic linkness. Here's a quick example. Now, the graph K6, we saw it's one of the graphs which are intrinsically linked. So for example, if I take K6 minus an edge, that is maximally non-intrinsically linked because there's only one way I can add the edge. And if I add any extra edge to that missing edge, then it will become intrinsically linked. So that's a quick example of maxnil. But, well, of course, it's not the only example. Let me show you this whole construction of how we can construct a full class of maximal link graphs. We're going to start with a maximal planar graph on n-1 vertices, because I want my new graph to have n vertices. So I'm taking a triangulation in the plane with n-1 vertices. And then I'm going to add to that a vertex v somewhere outside the plane. And I'm going to connect that vertex with all the vertices in the plane. So here's what I mean. Here's my planar triangulation. Okay, this is a planar triangulation with 9 vertices. And I tilted it a bit to be able to give a good perspective to this picture. So this triangulation, now it's pictured within the tilted triangle. And I'm adding a vertex which is not in the same plane where I realized this planar graph. I'm adding a vertex which I call V, and then I'm connecting with all the vertices in the plane. I claim that this type of graph, you can start with any triangulation here with any number of vertices. I claim that this type of graph, it's maximal with the property that it's linklessly embeddable. So it's what we call maxnil. Let's think about it. Well, by work of Sachs, and maybe we can kind of see here, such an embedding of a graph, it doesn't have non-trivial links, because everything sits in the plane except this vertex which sits out of the plane. There's no way you can create those two links that kind of are linked together. You need a bit more room. You want maybe a link to go under and come over the plane in order to create any linking. So this embedding as given, it's linkless. On the other hand, so this graph, it's linklessly embeddable. Why is it maximal? Well, let's think about adding any edge. I cannot add any edges at V because all the edges at V are already there. I could potentially add an edge within the planar part, but the planar part is already a triangulation. It's already maximal. So for example, if I add that edge there, the planar part together with this new added edge becomes non-planar. If it becomes non-planar, it means that by adding this edge, I must have created either a K5 or a K3 minor within this new graph with the added edge. Now, if I cone over the graph with this vector, with this new vertex V, by which it means it's the same, all the edges are still there. I added this new edge. I've created a minor which is either K5 added an edge, added a vertex. So I created either a K6 minor or a K3 minor. So adding any edge creates one of these two minors, and we saw these two minors were part of the Peterson family of graphs. So I just created intrinsic linkness by adding this edge. So this tells you that this construction always gives you a linkless embeddable graph, which is maximal with this property. Well, if you remember our discussion about planar graphs, we said that within a planar graph, we always had 3n-6 edges, if that was maximal for a triangulation. So let's see how this fares here. I started with a triangulation with n-1 vertices. So it has 3n-1 minus 6 edges. And to that, I added a new vertex. So now it has n vertices. And I added n-1 edges because I needed one edge to each of the planar vertices. So in total, this construction now gives the graphs with 4n minus 10 edges. So any such construction with n vertices has as 3n minus 10 edges. So this in a way mirrors the situation from planarity. It basically comes from that situation of triangulation. So we have a whole class of these linklessly embeddable graphs which have 4n minus 10 edges. Well, a theorem of Mader from 68, in fact, tells you that any more than this, so any graph with at least 4n minus 9 edges, necessarily contains a K6 minor. So in a way, in terms of number of edges, this is the most you can do. Anything above this number of edges becomes intrinsically linked because it contains K6. So the question now is, okay, this exactly mirrors the situation for planar graphs. Is this all that can happen? Is every maxnil graph going to have 4n minus, with n vertices, going to have 4n minus 10 edges? So, and the answer is no. So this is in contrast to what's happening to planarity. And examples have been known for some time. Here's an example. I take a triangular prism, which is a planar graph. I embed it here in the plane. And I'm taking two vertices, one which I put up, one which I put down. And I connect these vertices with everything in the triangular prism, but not connected in between them. And this, in terms of order, this is the smallest order graph. So n here is 8. This is the smallest order where you can create something that doesn't come from that construction I showed before. This is what that construction, because it had that one special vertex, those are called one apex graphs. So this is the minimal in terms of order example that doesn't come from that construction. It's not hard to show that in fact, this is linkless. This particular embedding is linkless. And also, if you add any edge, you will create intrinsic linkness. So this graph, it's maxnil. It's work of Jorgensen. So he was the one to first come up with this construction and to prove that this, in fact, it's one of these maxnil graphs. Of course, if you look at the number of edges here, you're not nearly close to 4n minus 10. In fact, this has 8 vertices and it has 21 edges. So the pattern here is 3n minus 3. Also, we can show, this is by work of Jorgensen and Bohm, who wrote this in a very nice way. We can show that we can construct, in fact, the whole family of these maxnil graphs by doing this following. I'm going to add a point to one of the edges, which is not part of the triangle in the planar part. Just add that vertex in and connect that vertex with the 2 up and down vertices. We call this operation a subdivision of the edge. So we're subdividing this non-triangular edge highlighted in blue. We're putting vertices on it, and then we're connecting. And this whole family of graphs is maxnil. It's a family of maxnil. And as opposed to what we had before with 4n minus 10, now all these graphs have 3n minus 3 edges. So kind of the lower bound, when the bound of the number of edges went pretty low with these examples. Now, our question was, we were working on this maxnil graphs for a different project. We were interested in the complement problem from this idea of linkless embeddable. And so if I look at a linkless embeddable graph, and I want to see whether its complement has the same property, then it's not a bad idea to take this linkless embeddable graph as kind of as fat as you can, so you can make the complement as small as you can, hoping it's linklessly embeddable. So this is how we came into this discussion about maxnil graphs, because we wanted to make one side of the equation as big as possible. And so we were wondering, well, is this all that happens? Is this family of 3n minus 3 kind of exclusive, or can we make this linklessly embeddable graphs even smaller, like smaller in terms of the number of edges? So we were able to tweak, with Andrei and Ramin, we were able to tweak that Jorgensen example and expand a couple of vertices in the planar graph, remove some of the vertices from top and bottom, and we build a family of graphs which now have 3n minus 5 edges. Well, it's not a big improvement here. It's not certainly a kind of an order of magnitude, but we kind of were able to build a family which was even less than what Jorgensen had before. And this works for any n. So again, it's an infinite family of graphs in any order strictly greater than 9. So we lowered this number of edges within the same order for maxnil graphs. Well, again, can we do better? Roughly, kind of at the same time, Max Ayres was at that time of Carnegie Mellon had a kind of a similar construction. He built a family of maxnil graphs, which considerably lowers the ratio. I mean, it lowers the ratio of edges over vertices. So now, in his examples, or family of examples, he started with n vertices, and he showed that he built an infinite family of examples for each n, which is mod 3, which is equal to 3 mod 10. So every other kind of 10th order. He built a family of this family where the number of edges was 14n over 5 minus 27 over 5. this is important because you see the ratio is suddenly not 3 anymore. In the limit, the ratio becomes 14/5, which is strictly less than 3. So this is a considerable improvement over what we saw in our previous examples. This only works for every kind of 10th order, but still it's the best we had at that time. He also proved, very importantly, at the other end, that a graph is maxnil, then it has at least 2n vertices. So he gave a lower limit for the number of, edges. He gave a lower limit for the number of edges. So at this point, we knew that the number of edges had to be greater than 2n, and at the same time had to be less than 4n minus 10. We had a lot of examples of 4n minus 10. We knew a few examples or classes of examples with 3n minus 5, 3n minus 3, and now max is 14n/5. So we kind of filled in some gaps in here. Still, we were wondering, can every possible number of edges be represented, or can I even have something with 2n? And in fact, we have something with 2n. It's a graph discovered by John Mahari. He wasn't interested in the number of edges to work this graph. This graph is pretty interesting by other means. Here's John's graph, which he calls Q13.3. So it has 13 vertices. You have a cycle on the outside, and then you have an inside cycles that kind of wraps around. You go always to the 4th vertex or 3rd vertex if you want, and you connect and you get an inner cycle. And this graph, it's maximal without a Peterson family minor. So hence it's linklessly embeddable, and it's also maxnil. This graph has 13 vertices and 26 edges because there are 13 cycles going around. So this shows that that lower bound that I gave earlier, that lower bound of 2n, it's attained. There are graphs which have this lower bound. Well, they're not attained in every order. For example, we check that you cannot do, at least for n less than 11 or equal to 11, you don't have such graphs. And we also check that for 14, for example, or 15, you don't have such graphs. So this graph is really, really special. And it's kind of an open question whether more such graphs exist. And I'll come back to that towards the end. Now, how does this graph help us to fill in this gap between 2n and 4n minus 10? Or in particular, if we can lower this edge to vertex ratio any further. Remember, before it was 3, now it's 14/5. So we're wondering how low can you get? So ideally, we could find a whole family of graphs where the edge to vertex ratio is 2. So a whole family of these Mahari graphs. But so far, here's what we were able to find. So we were able to show, we were able to show that for each n greater or equal to 13, there exists a family of maxnil graphs with n vertices, which have less than 25n/12 minus 1/4 edges. So this is a considerable improvement over Iris's bound, or let alone the Jorgensen bound of 3, which we had before. So 25/12, it's still greater than 2, but we're kind of getting very close to that lower bound of 2. So I'm going to give you an idea of how we kind of build these graphs, this family of graphs. And as opposed to Max's examples that only worked for every 10th order, this construction works for any order greater or equal than 13. Now, the idea of this construction has to do with gluing smaller maxnil graphs into making larger maxnil graphs. Now, as we were working on maxnil graphs, before even coming to the question of the number of edges, we were interested with Andrei and Ramin. We are really interested in the structure of maxnil graphs, really connectivity. Can I do click sum of these graphs in some way to build a whole family? So we were able to show a few results, which are not mentioned here because they're not needed, but I'll maybe just tell them briefly. We know how to glue, for example, two maxnil graphs over an edge. We know exactly, if I take two maxnil graphs and I identify an edge together, I know when I create a maxnil graph or not. I know how to do a click sum over a triangle. And I know exactly if that gives me a maxnil graph or not. So if I have a graph on the right, and if I identify a triangle, and I have a graph on the left, and I identify a triangle in that graph also, and I put these two together, kind of doing a click sum of the two graphs, I know when that's maxnil or not. And I also know what happens when I connect over a K4 subgraph. So all these were kind of knowledge we already had as coming into this problem. The only one that's needed for our construction is the case of connecting over a K2. So I'm going to just list that part of the theorem. If you start with two maxnil graphs and you pick an edge in each, and then you do a connect sum over that edge or a click sum over that edge. So literally you have a graph, which we call G1, and I identifying an edge E. And I have another graph, which I call G2, and I identify another edge, which I call E. And then I'm gluing these two graphs by literally identifying those two vertices and just keeping one copy of that edge. And that's a K2 click sum. And we know that if you start with maxnil graphs, G1 and G2, this operation will again give you a maxnil graph as long as E, that edge which you identify on both left and right, is not triangular in at least one of G1 or G2, so, which non-triangular means it's not part of any triangle. So for example, here you notice E is not triangular in G1. If the edge E is triangular in both, you still get a linkless graph, but it's not maximal linkless. You can still add edges to it and be linkless. But if the edge is non-triangular in at least one of them, then you're for sure going to get a maxnil graph. So here how we use this theorem to construct our family of graphs with low number of edges. So we started from the Mahari graph, Q13.3. Again, this has 13 vertices and 26 edges. We started with that graph. And here's kind of a silly thing you can do. You can do this click sum of the graph, Mahari graph, with a simple triangle. Okay, what's special about the graph, in fact, and this is the key property here, no edge in this graph is part of a triangle. So this graph itself as a whole is non-triangular. So no edge in this graph, it's part of any, there are no triangles in this graph. So now if I identify, for example, that edge there, it's a non-triangular edge in a maxnil graph. And the triangle itself, it's a maxnil graph in a trivial way. You cannot add any edges to it. So now if we apply our theorem from before, I can glue this triangle onto that edge, make a K2 click sum, and I obtain a new maxnil graph. And I can do this. See, I can do this on any single edge of this graph. I can add triangles like this, and these new graphs will still be maxnil. Of course, once you use an edge that it becomes triangular, any edges you use still are already triangular. So this construction will not go on forever. But what's nice to remark about this, at least as much as you can do that, notice that with every triangle that you add exactly one vertex and you add 2 edges. So you started originally with 13 vertices and 26 edges. By adding a triangle, you now have 14 vertices and 28 edges. And this keeps going. You can add as many triangles as original number of edges, which was 26. So you can keep this construction going until you have 39 vertices and 78 edges. And all of these will attain that lower bound of 2n vertices. N vertices and 2n edges. So this goes pretty far, but not far enough. Because at this time, once you reach 39, you have a maxnil graph with all triangular edges. So you can no longer further this construction with a triangle. But we can still do something, which means maybe by doing this, we cannot get the absolute lowest bound of 2n, but we can tweak this construction a bit so that we get our found lower bound with 25 over 12. Okay, so here's what we did. Well, if you take if you just take 2 of the Mahari graphs, these are still maxnil, and you can identify an edge in each, and you can click sum over that edge. You suddenly have a new maxnil graph, which has a lot of non-triangular edges. The issue is, or maybe the disadvantage in doing this here, is that you see, when you did the click sum, you lost 1 edge. So you decrease the number of edges by 1, because when you identify, you delete double edges, but you lost 2 vertices. So doing this kind of gluing, it's not as efficient as before. If you lose a vertex and 2 edges, you're increasing the ratio of edges to vertices. So that's not exactly what we want, but we have to do that if we want to at least further this construction. So here's what we did. It's a combination of gluing this way and adding the triangles. Remember, adding the triangles keeps the bound low. So you want to be able to add as many triangles as you can. So what we did is we identified this number, which is n-3, ceiling of n-3 over 36. So if you want to construct a big graph with n vertices, you need at least k of these Mahari graphs connected to each other. That's the least, or the least you need, okay? So we identify this number k, and we glued k copies of the Mahari graph. You glue k copies along an edge. This example only glues 2 copies, but you can imagine you have another copy kind of maybe sitting in the back somewhere, which also has the edge identified. So we glued all this together like a fan of graphs. And then we started adding triangles along the edges. All the edges to start with are non-triangular. So you start adding edges along, triangles along every edge. And we get this big graph. So just by gluing, this is an easy computation. You have 11k plus 2 vertices and 25k plus 1 edges after you glue k copies. And then we add as many vertices as we need to get a graph with n, which means we add 2 edges for each of this number of vertices. So we get a graph now with n vertices, and a quick calculation will show that you get at most 25n over 12 minus 1/4 number of edges. And this is, as far as we know, kind of the lowest bound we have for an infinite family of graphs, which are maxnil, a lowest bound on the number of edges. So it's still an open question whether this edge to vertex ratio can be made even smaller. I mean, 25 over 12, it's pretty close to 2, but potentially you can make this smaller. A way to make this smaller is to find one of these Mahari-like graphs which have more vertices than 13, because that will require you to do less of the gluings, and it will preserve the lower bound for longer if you have more vertices than 13. But we are kind of in the process of checking. We couldn't find with 14 or 15 or even 16. There is some computational kind of power which has some upper bound there. But if we can find larger graphs of this type, then this will further this construction. And I guess a good question would be, can you find an infinite family of graphs which attain this, which attain this 2n lower bound on the number of vertices? So these are still kind of open questions. I think it's the subject, it's very nice and geometrical. And I'm going to stop here and thank you all for your attention.
Let's thank the speaker. And are there any questions? Maybe I can ask one if there are no questions. Yeah. So do you, I think you already touched on this. You said, I was going to ask, can you do click sum with other maxnil graphs and try and get, more examples? And I think you already said that you were doing this. Have you thought about so instead of maxnil graph, like a min-nil graph, where you're looking at minimally 3 connected graphs with this property? So it's a maxnil is, like one side, the maximum, and the minimal ones.
Well, I'm guessing the worry there is to preserve connectivity, because once you have a nil graph, you can just take away edges from it, and it will be a subgraph, so it still remain nil. But that's a good question. You want to take this graph, they will remain nil, but you want to keep this 3 connected. So we haven't thought in this direction, but that's a good point.
Are there any other questions?
Yeah, I was wondering, I'm curious, the proof techniques, do you mostly just able to get by with just using a minor theorem, or do you actually have to get nitty-gritty and deal with the topology and stuff like that?
So for this, we were able to use the minor theorem, because for intrinsically linked graphs, we knew the set of excluded minors. So for example, when we had those examples where we were kind of putting vertices up and down, we were able to show there's a lot of symmetry to the graph, but we were able to show that in any way you add an edge, you have to create one of these minors in the Peterson family. It's not always a K6, it might be some triangle Y move from K6, but we were able to identify a minor within the Peterson graph. So it's more, in that aspect, it's more combinatorial than topologic, just identifying the minor.
Thanks.
I have a question that's maybe a different, sort of more topological generalization. Do you know if people have looked at, are there graphs that are intrinsically say like Borromean ring linked in the sense that they're not intrinsically linked, but you have to have a set of like 3 disjoint cycles that form Borromean rings in any embedding?
I think you could have that, but in the kind of main proof of the theorem, it's intrinsically linked because overall, if you look at all the cycles, you have an odd linking number. So you're looking at all possible cycles that can link to each other. And if you add all this, there's the idea of a linking number. For example, these, if you just do the basic, they will link once. The Borromean rings, if you look at pairwise linking, that's linking 0. So there may be a Borromean link, but if it's intrinsically linked, it's because it also has some other link in it. And also,
yeah, I meant like the class of graphs that are, I guess not intrinsically linked, but
it's not possible. I get it now. So there is this other result of Robertson, Seymour, and Thomas, which says that if you're not intrinsically linked, then you have what's called a paneled embedding. And the paneled embedding, it's an embedding where every cycle bounds a disk which doesn't intersect the rest of the graph. So I think if you have Borromean rings, you cannot have a paneled embedding in an embedding. That embedding which has the Borromean rings, it's not paneled. So if it's not linked, there'll be another embedding when you don't have the Borromean rings.
Oh, okay, so you can't intrinsically have the Borromean rings.
Exactly.
Oh, cool. Okay, thank you.
That's a very nice question.
Are there any more questions?
Can I ask, first of all, very nice talk and nice to see you.
Nice to see you, Mio.
How are you doing? Yeah, good.
Good.
So are there other kind of maybe embeddings, into higher dimensional Rs, or maybe in 3 dimensions, but other kind of embeddings of graphs that might be of interest, and then you could, and maybe similar questions can be asked about them. I'm assuming that eventually any graph could be embedded in high enough dimensions without any links, but there's probably some kind of a borderline where this property breaks down for any given number of vertices. Or
I think for intrinsic linkness, once you go to 4 dimension, since any 2 curves in kind of closed curves in 4 dimension can be separated, this kind of intrinsic linkness breaks immediately once you go in the upper dimension. But there are other questions. So in 3 dimensions, you can talk of other properties. For example, a more complex property or more complicated is intrinsic knottedness, where you take a cycle within your graph and you're asked if that cycle is just a circle or if it's knotted in some way. And that's also a property that's closed undertaking minors, and which means that it also has a finite set of excluded minors. But for that property, the finite set of excluded minors is not yet known. So with Andrei and Ramin and Thomas Matman from Chico, we are working on kind of the next level up of property, which is intrinsic knotness. It's very interesting that we know hundreds of minor minimal intrinsically knotted graphs, but we don't know if that's everything there is. So we're trying to connect with other kind of graph properties and see if we can solve that problem. But again, this new property, when moved into 4 dimension, it kind of unravels because you have no more knotting.
I assume there's a lot of also computer calculations involved in some of these, or
there is a lot of computer calculations. Yes, but everything that everything for today's talk was done by hand. But as we're trying to
find examples,
work larger examples, then we need a bit of computer help.
Nice, nice.
And when you say knottedness, are you thinking of any particular knots or just a different sense of knotted?
No, like not any particular knot. There are, for example, if you take a K7 and you embed a K7, if I remember correctly, you can always show that there is a Hamiltonian cycle, which is 8 knot. This knot with just 4 crossings. But then other graphs might have embeddings where knots are just trefoils, kind of the easiest unknot. So yes, the family of knots can kind of vary across. It's not for a specific knot.
Are there any more questions?
Is there some I don't know, philosophical reasons for maybe expecting that the sect of excluded minors would be still of some kind of complete or bipartite or some K ABC type of graphs or something? I mean, this is just, or is it just a complete happening here?
So we have
planarity and this situation you have this.
So the situation you're asking for knottedness?
Yeah, knottedness or maybe other type of embedding.
Yes, so for planar graphs, we had K5 and K33. And this can be general, I mean, one up, you go to K6 and K331. And then if you add one more vertex, you get K7 and K3311. You add one more vertex to these. And both these K7 and K311 kind of generating from this construction are known to be intrinsically knotted. So there are generalizations there. But then there are many families outside of these. So for intrinsic knottedness, linkness, you only had K6, and then you do the triangle Y moves, and you have the whole family. For knots, you have already 2 families, and you can do triangle Y moves, and you get more of them. But there are a lot of others which are not here. So you have that part solved, but there's a lot of unsolved graphs.
All right, thank you.
Welcome.
This was very good. I really enjoyed it. Let's thank the speaker again.
I'm happy. Thank you.
Thank you.